Hi guys, I'm going to be looking at question 7 from the problem solving / skills section we looked at, just the last question. I'm not going to worry too much about the first couple of parts because they were reasonably straightforward. It was just requiring you to know that we needed to presume independence and it wasn't stated in order for it to be binomial, and that the conditions were met for a Poisson distribution. I'm in this body here. The first one asks us to find exactly one of the the pixels was faulty. So all we needed to do was put that then in our Poisson distribution by doing e to the minus lambda times by lambda to the power of 1, 15.6 to the power of 1, all over 1 factorial. That would have worked that one out for us to be... here it is. To be 0.328, rounded to 3 significant figures. Similar idea for y being bigger than or equal to 2. We needed to do 1 minus the probability that it was equal to 1. Also take away the probability that it was equal to 0. That was the only way to do that question, as we couldn't use our tables. So we have previously worked out y being equal to 1, which was great. But I also need to do this one. So e to the minus lambda times lambda to the x over x factorial. Being careful not to be afraid of 0 factorial, dividing by it. 0 factorial is 1. I know it seems a bit strange, but it is, so it still works. So all I needed to do was 1, take away my answer, keeping answer in my calculator rather than rounding it, taking away e to the minus 15.6, and we got 0.672, again, 2, 3 significant figures. Okay? And then for part 3, it asks us to talk about the fact that in a batch of 5 monitor screens, we needed to, so in a batch of 5 monitor screens, we needed exactly one of the 5 to have at least 2 things. So that then becomes a new variable, so I'm going to call that z, and this variable is binomially distributed with 5 screens, and then the probability of success becomes there being more than 2 pixels, so that becomes this probability here, so 0.672. And I wanted the probability that exactly 1 of these, so again, just putting that in the binomial distribution. 5C1, probability of success, in this case, is more than 2 faulty pixels, so it's 0.672 to the power of 1, and our probability of failure is 1 take away that, so 0.328 to the power of 4. I'm going to keep the answer bit in my calculator here and just do 5C1, which I know is 5, times by the answer from before to the power of 1, times by 1 minus the answer from before to the power of 4. So you can see that on my calculator, that's what it looks like. I've just kept that answer in there to ensure that I've got accuracy involved, and I get 0.0388. Again, to 3 significant figures, keeping my accuracy consistent throughout. Okay. Then when it came to part 4, part 5 now. Oh yeah, I've got 1, 2, 2, 3. Oh well. So part 5 asked us, what would the probability have to be in order for the probability of there being exactly no faulty pixels to be 90%. Okay? So this had nothing to do with this binomial distribution, it was also with the original distribution. Okay? You can do this in terms of binomial, or you can do it in terms of Poisson. It makes no difference because your degree of accuracy is pretty close, because the n is large and the p is so small that it's pretty much a perfect approximation from the binomial to the Poisson. So I would use either in this case. And all I'm going to say is the probability that x being equal to 0, I'm going to call it y because I'm going to use the Poisson one. I'm just a little bit more comfortable with it. And I need to say that the probability of e to the minus lambda, lambda to the x over x factorial is equal to 0.90. And ultimately I want to find that lambda. And so the lambda to 0 is just 1, 0 factorial is just 1, so it's literally just e to the lambda is equal to 0.9. So lambda is the negative ln of 0.9, and we get 0.10, I think, for that one, which are two significant figures. Then, if I know that that's what my lambda is, I need to remember that lambda is just n times p. So lambda in this case needs to be 0.1. N still needs to be the number of pixels in the computer screen, and then p is going to be our new probability that that's the answer that we're looking for. So p is just minus ln of 0.9, keeping it accurate, dividing it by 780,000, and I get 0.00000135, otherwise known as 1.35 times 10 to the minus 7 to 3 significant figures. Okay, that is the probability that we are looking for. Okay, so it's all to do with the fact that you could have either found the p from the binomial distribution, or you could have done it in terms of this. This one becomes a little bit easier to do it in terms of the Poisson, especially if you previously approximated, because this concept will only work if we're looking for exactly equal to 0. Otherwise, we need to use our factorial with an unknown n in it, and it just becomes quite complicated. So I would always aim to solve these with the Poisson if possible, and it's literally just finding the lambda and then working backwards to find your n or your p, whichever one in the question you need to find. Okay. I think some mistakes were lost in this because of the complicated numbers. Some mistakes were made from rounding too early and then using previous parts in the next stage of your working. So again, my advice is to do what I do with my calculator and keep your answer in as much as possible. Okay. I hope that helps. The question on the diagnostics is very, very similar to this. So if you're watching this, taking note, and thinking about each stage, then I'm sure you'll do absolutely fine.